Let's start this probability module by taking a look at one of the most classic probability examples that's out there. This is called the three-door game or the three-door problem, and maybe you've also heard it described as the Monty Hall problem. And it's sometimes described as the Monty Hall problem because the game is based upon the game show that Monty Hall was the host of, and that was Let's Make a Deal, and that was a really popular game show back in the 1970s and early 80s. And this game would be what they would play at the very end of the show. And typically what they would do is they would do something like this. Monty Hall would ask a contestant to pick a door. And so let's just pretend that we're playing the game and we're the contestant, and I'm going to pick door number 1. Now you're going to see as we're playing this game that another door is immediately revealed as soon as we pick door 1. And that's because if you were the contestant on the game show, Monty Hall would say to you, okay, well you can keep what you have behind door 1, and you haven't seen it yet. Or you can take the chance of switching to door number 3, and in either case, you're kind of risking getting what you have behind door number 2. And you can see here that we've got a goat behind door number 2. And for some reason, when you play this game, and when they played Let's Make a Deal, they would have kind of obnoxious losing prizes behind 2 of the doors. So as you play this game right now, you'll see that the winning prize is a car, and then the 2 losing prizes, or the prizes behind the 2 losing doors, are goats. Now, the big question, though, is from a probability standpoint, does it make any difference whether we stay with our original choice or switch to this one? And a lot of people would look at this and say, well, no, there's only 2 doors. You've got door 1, you've got door 3, and the winning prize is behind one of those doors. But you'll see as we go through this simulation right now that there actually might be a strategy that you can use. So let's play this a couple times and then simulate it a whole bunch of times and see what that strategy should be. Okay, so again, I've selected door 1. We can stay with door 1 or we can switch to door 3. And in this case, there's no reason to why I'm doing this, but I'm going to switch just to see what happens. And so in this case, I switch and I would lose. And so maybe you're thinking now, okay, well, maybe you should stay then, and that's going to be the strategy. Well, let's play it again. Okay, let's pick door number 1 again. You can see that door number 2 is revealed, and so we can either stay with our original choice or switch to what we have behind door number 3. And you know what? Just for the fun of it, I'm going to switch again. And this time, I would win. So now you might be really confused and say, well, gosh, you know, the first time we won by staying, or we would have won by staying, and the second time we won by switching. And so let's play it again. And again, let's pick door 1. And again, I'm going to switch. And there you go. This time you can see that I did win again by switching. So 2 out of the 3 times that I've played this now, I've won the game by switching from my original choice. And so again, I ask you the question, does it make a difference when you're playing this game and you select a door? Does it make a difference whether you stay with your original choice or switch to the second door? Let's do this. Let's simulate now. So you can go down here and press the simulate button. And by the way, the link to this is in your notes. I'm at mathwarehouse.com/Monty Hall simulation online. And so when we simulate this, we're going to be able to play this many, many times, and then you'll be able to clearly identify what that strategy should be. So let's run the simulation 100 times right now. You can click on this and you can see that you can actually run it 500 times or 1,000 times, but I think you'll get the main point even if we run it 100 times. And each time that we run the simulation, it's going to take our door and it will allow us to either keep the door each time out of all 100 simulations or change our choice each time. And since I was changing my choice a lot as we were going through it in the beginning, let's just stick with that. And let's press Start Simulation, and then we can observe here how we're going to win. Are we going to win, or what are we going to win? Are we going to win the car by changing our choice these 100 times? Are we going to win the car more, or are we going to win the goats more? In other words, are we going to lose more? And as this plays out, you can see right now that we're winning the car more often than we are the goats. And so maybe changing doors is the better bet. Maybe that should be the strategy. And you can see that 57% of the time when we changed the doors, in this case, we were winning the car. Okay, let's do it again, but this time we're going to keep our choice each time. And let's simulate. Again, this is doing it 100 times. And you can see it's kind of the reverse. And so it looks like you're winning the goats, or in other words, you're losing more often when you're keeping the choice. And the percentage of times that you are losing appears to be somewhat around the percentage of times that we were winning before when we changed doors. And you can see, in fact, that as we get through 100 simulations, that in this case where you kept your choice, you would lose 61% of the time, and you would win 39% of the time. So just going between these couple of simulations, and we've only simulated 100 times each, in each scenario where we would change the choice each time or keep the choice each time, you would probably look at that and say, okay, well, it looks like the strategy would be that you should change doors. And that is exactly correct. Given the context, given that Monty Hall knows exactly where the winning prizes are and the losing prizes are, and given what we're seeing in the simulation here, if you're playing this game, you absolutely would want to change doors. Now, let's see if I can illustrate it a little bit more. I'm going to run the simulation 500 times, and I'm going to press simulate, and this time we are going to go back to changing doors each time. So as I press simulate, let's continue to watch what happens with our percentages. Now it's kind of slow, this process is a little bit slow, but what you should see as the number of simulations increases is you should see the percentage of time that you're winning the car is actually going to be really, really close to 67%, or 66 and 2/3%. You should be winning the car by switching 2 out of 3 times. So if you are offered a door and then you're offered to either stay with that door or switch to another door, you will win 2/3 of the time by switching, and you will win 1/3 of the time by staying. But since you would win 2/3 of the time by switching, the general strategy that you would take in a game like this would always be to switch. And you can see that as the number of simulations continues to increase, look at those percentages. Like I said, this is going to converge to 66 and 2/3%, and then this is going to converge to about 33%. Now, just because I'm showing this to you in the simulation can sometimes, just lead to even more confusion. And I want you to have a little bit of more of an understanding of it. And so I guess I should say, first of all, that it is always good to go to a simulation and utilize that simulation to help your understanding of probability. Sometimes probability can be very difficult to grasp, and simulations are used all the time in statistics. Now, there's other ways of thinking about this theoretically as well. And so let me just stop this at this point, and let me just go back to the door, the 3 doors, and just mention a couple of those other ways of thinking about this. There's also a very good link that you should check out that's in your notes that goes through an alternative explanation that I'm not going to talk about in this video, but offers a really nice way of explaining or justifying why switching is the best choice. So here's a very simple way of justifying why switching is the best choice. When you picked door 1 initially to start this whole thing off, or if you picked door 1 initially to start this whole thing off, what is the probability that the winning prize, before anything is revealed, what is the probability that the winning prize is behind door number 1? Well, you have 3 doors, and therefore you would have a 1/3 chance that it's behind door 1. And so what's the probability that it's behind these other doors? Well, the probability that it's behind the other doors would be 2/3, because there's 2 doors here. So if I offered you your original door, or if I offered you both of these other doors, which one would you take? Well, you would take both of the other doors, even knowing that one of the doors in these 2 right here would still be a losing door, but you would rather have 2 doors over 1 door. And so that's kind of like what this is like in the beginning. When you're offered your 1 door, you could think of it as, okay, well, I have a 1/3 chance of winning. And if you switch, then you should have a 2/3 chance of winning. And I know it does not look like you would have a 2/3 chance of winning because one of these other 2 doors has been revealed. But again, one of those other 2 doors must be a losing door. So if you pick one door initially and you're offered to switch, it's almost like they're saying, okay, you could have that one door originally, or you could have the other two together. You would always take a 2/3 probability over a 1/3 probability. Another way to think about it is like this. I'm kind of listing out all of the possibilities here. And when we get into some upcoming videos, you'll see that this is actually a really good strategy for addressing probability examples. We talk about listing out things such as the sample space and all of that. So here's all the possibilities. You can either have a car behind door number 1 and then goats behind doors 2 and 3, or you could have goats behind doors 1 and 3 and a car behind door 2, or you could go goat, goat, car. So let's go back to the case where we selected door 1. So when we selected door 1, think about this. We don't know what's behind door 1. But if this is the setup right here, if it went car, goat, goat, would you win by switching or staying? Well, if this was the setup, you would actually win by staying. If this was the setup right here, would you win by switching or staying? Well, you could see that in this case, you would obviously be wanting to switch. And notice that this would be the scenario where Monty Hall would actually be revealing this goat, and then you would be looking at this and you'd be saying, okay, well, I can either stay with this choice or switch to this one. And you can see, again, if you switched, you'd be winning the car. So here, in this scenario, you would win by staying. In this scenario, you would win by switching. And in this scenario, you could see that, again, you would want to switch to door 3 because door 2 would have been revealed to you. And that switching to door 3 would have won you the car. So the big thing to recognize here is that out of the 3 possible scenarios, that you win by switching 2 out of those 3 times. And so again, this justifies the fact that when you're playing this 3-door game and you're offered that original door, or you pick that original door, and then you're offered an opportunity to stay or switch, you would always want to switch. Check out that link that you see in the notes. It's a really neat way of thinking about this. Instead of talking about the 3-door problem, they talk about the 100-door problem. And again, it really puts things into perspective. So hopefully this just gets you thinking a little bit and gets you excited about some of the interesting and fun examples that we'll be doing throughout this module. So thanks for checking it out.